So we want to solve the following problem. Here is given a training set which happens to be linearly separable, but that will not be necessary for the derivations and computations that we do. And here are now two different solutions, which, by the way, happen to be optimal for their respective margins. So here I specified that the margin should have a width of 2 fingers, and this is the best solution that you find. And in fact, this is some kind of extreme solution, as you can see, because if I twisted this decision boundary any other way, some of the observations would infringe on the margin and would thus contribute to the empirical error. Right now, if you look at this solution, it has exactly 0 empirical error as measured by the hinge loss, because these points here, which have been circled with a yellow circle, they're right at the margin, but they haven't started walking into the margin or even started walking on the wrong side of the decision boundary. Now down there, I specified a margin that would be a hand span, and again, this is the best solution that was found. And this time you see that, well, you know, necessarily some of the observations now lie in or on the margin, and if you look closely, one of the observations is now even on the other side of the decision boundary. Now, which one do you like better? Which one do you like better? So if you look at if you had to describe this data set to a person on the phone, I guess you would say that the blue points are on the left and the red points are on the right. So given that we have very few points in this feature space, I think we would expect a classifier that is roughly vertical, like the one down here, and that says the one class B here and the other class B there. This, on the other hand, it's a perfect fit to our training set, but the precise position that we got out really depended on the exact configuration of these points here, which have been circled. So if you imagine having a little bit of noise on the data, or if you imagine getting another training set from the same source, you wouldn't expect to be the points in the exact same position, but you would still expect the blue ones to be on the left and the red ones to be on the right. So I would argue that this is an overfit, and this is a more sensible solution. Even so, this it's some kind of extreme solution. It's called the hard margin SVM, because this is it has the widest possible margin that you can get without having any of the training set enter into the margin. So getting this solution is of some interest. And that is also of interest in the sense of looking, more sensible and more what you would want to have in the end of the day. This is a regularized version, and this is a soft margin support vector machine. And we will now first look, given a specific margin of either 2 fingers or a hand span, how do you find the optimum solution? And later we see, or we discuss, how do we find in general what is a good margin? Okay, and I need the camera here, please. So in technical terms, we're now looking at the linear soft margin SVM. For starters, we assume that the margin M is given. And given this margin M, we now want to find the optimum parameters, the normal vector. I'm writing W tilde because I want it to be normalized to 1. We want to minimize the empirical error, which depends on the normal vector. And so it depends on normal vector and on the bias of my decision boundary, and of course on the training set, but I'm not writing the training set down here. I have n observations overall, so the total empirical loss is given by the sum of the hinge losses for a margin M. And I wanted the norm of W tilde to be 1. If I did not have this constraint here, I could satisfy any margin or make this empirical loss, at least for linearly separable problems, arbitrarily small by letting my normal vector grow and grow and grow. Now, another formulation of the same problem, I'm coming back to this picture that we painted here. Another formulation is in terms of these green lengths here, and they are measured by slack variables, which in this field are typically called psi. Okay, so the distance of an observation from where it should lie, so from decision boundary plus margin, is the slack variable psi. So I can write that I want to minimize the sum of the slack variables, and these slacks are necessary such that all samples lie on the, we don't want the samples only to lie on the correct side of the decision boundary, we want them to lie on the correct side of the decision boundary plus a safety margin of M. However, I admit some slack, so I allow some of the variables to violate this constraint by subtracting here my slack variable, and one slack variable is associated with each observation. They all must be non-negative. And I had stipulated that the norm of W tilde should be 1. And in this equation here, you can see more clearly why this was necessary, because if I have specified the margin, and let's assume that the problem is linearly separable, then by just growing W tilde in length, in norm, I could always make each of the linearly separable observations, I could always make them satisfy this inequality. So I need to add this constraint. However, unfortunately, in the space of all W's, so let's say we have a two-dimensional problem, this constraint here means that W must lie on a circle. And you see that a circle is not a convex domain. And in optimization, it is, first of all, unpopular to have non-convex objective functions. Here we don't have the problem. We have a linear objective function that is very nice. We have a linear inequality, which is okay, a linear inequality, which is okay. And then we have something that's non-convex. People don't like that. So instead, we relax this constraint to say that the norm should be less than or equal to 1, meaning that our solution doesn't have to reside on the circle anymore, but it can now lie anywhere in this disk. That's what this constraint says. But of course, these other constraints will further restrict the disk in some ways. By the way, so introducing this inequality instead of an equality, depending on the other constraints, it can really change the solution a little bit. Now, if this was the only constraint, so if I didn't have, let's say, these other constraints here, the solution would be the same, Because if I have a linear objective function and I constrain the feasible space to a disk, then the extremum of this objective function inside the disk would always be somewhere at the limit of the disk. So it would be on the circle. However, introducing these additional linear inequalities here mean that I can perhaps get out a solution, an optimal solution that will no longer lie on the circle. It could also lie somewhere inside. I'm just mentioning this in much detail because usually when you read about support vector machines, so people don't start here or they don't start there. They start with an equation that's even a little bit different, which we will see in a moment. Okay. Yes, question. Why do I put the tildes? Just because I want to get rid of this constraint, and I don't want to keep writing tildes for the rest of the day. So I'm I'm doing tildes now just to omit them later on. Also, why am I not using homogeneous coordinates this time after advertising for them last week? The reason is that we will later on introduce some regularization, but we want this regularization to affect only the normal vector, not the bias. And this is why I'm now going to all these lengths and putting all the b's and the tildes. Okay, so let's get rid of the tildes. I now posit new w, which is w tilde divided by the margin, and a bias, which is b tilde divided by the margin, and a slack variable, which is the original slack variable divided by the margin. And I can then write the following optimization problem. You see that the inequality which I'm writing right now is the same as the one we had before, except that it has been divided by m and the tilde is removed. So on the previous page, here we had lots of tildes and an m, and the m is now gone. I still have this non-negativity constraint, and this time I can write that the norm of w should be less than or equal 1 over the margin. Now, by the way, this constraint here is still a nuisance. It's still troublesome. Now it has become convex. It is a disk. But in optimization problems, we would like to have just linear inequalities, just because it makes the life of an optimizer easier. So we will get rid of this thing also in the end. But for now, this is the problem that we want to solve if we are given m. So given the margin m, we have now formalized how to find the optimal classifier. And if you look at your handout again, what you see in the top right corner is the space of all classifiers. You see the axes are W1 and W2. In fact, for this plot here and for my convenience, I have forced it to go through the origin. So I set B to 0. But this is the hinge loss of all classifiers. And if we now change the length of the normal vector, that amounts to changing the length of the margin. Okay, if you remember this constraint here, the margin was given, and if I specify the margin, it means I put an upper limit on the length of my normal vector. So in particular, large margin means that we want a short normal vector. So let's look at this picture again. So red means high empirical error, blue means low empirical error. Generally speaking, what this tells you is that all of this plot here is for the training set that's shown here. What this tells you, first of all, it's a bad idea to have the normal vector point leftwards. So the worst possible classifier that you can possibly produce is one that misclassifies all samples. It would lie here, but it would point the wrong way. So it would say red class is here, blue class is there. That's the worst you can possibly do. And that will give you these very high empirical errors. Now, on the other hand, if your classifier or if your normal vector points somewhere to the right, this will give you, if you just look at the plot on a very coarse level, you get dark blue values. It means, generally speaking, this looks good. This will give you low empirical error. But now you can ask in more detail, what will give me 0 empirical error? And in fact, if you look closely, I've plotted some contour lines here for low energy values. And there is one contour line, which I'm not sure you can see on the beamer. It runs roughly like this. And this contour line means that in this area down here, in the version space, you have 0 empirical error. So down here, this is version space. Those are all classifiers with 0 empirical error. And version space is a technical term. Now, please try and explain to me, what these classifiers are that live in version space. So what does it mean in terms of the margin? What does it mean in terms of the classifier that we have here relative to the training set? Maybe. Come on.
So those classifiers have a normal vector W, which is pointing down to the right, which means that it looks like the hard margin classifier.
Yes.
And the longer that vector is, the smaller the margin, so the more play it has.
Exactly. Exactly. So that's just like you said, if we let the norm of W grow, this corresponds to ever smaller margin. So let's say if we consider the classifiers that lie on a circle here far out, so classifiers with a very narrow margin, then there are quite a few, and they live here in this part of classifier space. Then we have quite a few classifiers with exactly 0 empirical error. Now kind of I'm getting too short here. So you see these classifiers, they all have 0 empirical error as long as we require no margin. And among all these classifiers from version space, there's one single one that is particular or that is unique, namely the one from all these classifiers with 0 empirical error, there's one which has the widest possible margin, which was exactly the one shown here. And coming back to this picture, from all of version space, this is the one classifier that has the shortest norm, or the normal vector with of shortest length. It's actually that point here. So the hard margin SVM tries to find from version space the point which is closest to the origin. But now we can push even harder and we say, I want a wider margin than this. So I can start to, well, shrink the disk of admissible classifiers. And as I shrink the disk, I will follow a path of optimum classifiers that goes roughly like this. So my margin will become wider, and my normal vector will tend to point more and more simply to the right-hand side rather than to the right and down. And that goes, by the way, with this plot here. So there's again a lot of information here. The black curve in this plot here shows you the empirical error of the optimal classifier as I let the margin become, well, wider or narrower. So as long as I do not exact, as long as I do not demand from my solver to produce a wide margin, I get 0 error. So this is version space, or these are all the classifiers in version space. And now as my margin becomes wider than this point, so wider than the margin found by the hard margin SVM, my empirical error starts to grow. So the values of the curve here are essentially given by the hue, by the color in this false color plot, as I search for, the path of lowest energy, if you wish, subject to this constraint of ever shorter norm on my normal vector. So there's the black curve, and the hard margin SVM classifier lies here. This is the one that we want to find. Now, I could either, at least as I work with low dimensional data, I could, hand tune my margin until I find this solution and this sweet spot here. Or, of course, we want to do it automatically. And one way of doing it automatically is the following. Namely, we can add something to the black function, some other function that increases for decreasing margin. And one such function here is shown in red, but you can think of many different functions. So, for example, if I just chose a function that increases linearly with decreasing margin, and if I added this to the black line, this would give me a new function with a local optimum right there. So the trick is to add a little bit of a function that grows for decreasing m, and to then find that local optimum. And that will give the margin of the hard margin SVM, and plugging that into the optimization problem that you've seen, it will give you the actual classifier. Now, there is much freedom in which function would you like to add here? What red line would you like to add to the black? And so this is not, there is no deep truth in which function you choose here. However, it would be nice to have one that's computationally convenient, and that actually happens to be the red line here, and you will see in some time why this happens to be computationally convenient. And so if I now take the sum between the red and the black line, or I've multiplied them with different constants that are chosen by me, the user, I obtain this set of green curves here with their respective local minima. So if I admix very little of this red line, which represents a regularization, if I admix very little of it, then I will obtain the hard margin SVM. And as I start regularizing more and more, the minimum of my sum or of my joint function will shift to ever larger margins. So what kind of function would we like to have? In W space, you would like this. Well, there are essentially two things that are sensible to do for this regularization. Most people would prefer to use as a regularization function one that is isotropic. So you want it to be round or symmetric with respect to this center here, because this would only impose a tendency or a bias towards shortening the parameter vector without, however, biasing the direction in which it should point. However, there are other ways of regularizing. In particular, if you use something that favors the axis, so like the L1 norm rather than the L2 norm, you would then obtain a solution which preferentially has one of the two components going to 0. So you would then obtain a solution that's sparse even in the primal domain. Now that's a lot of information. We will go over it again. Let me, because this is a lot of information and because we should chew on this for a while, I will do a short digression here. This digression has to do with model selection and overfitting bias variance trade-off. Ein Exkurs auf Deutsch. So if I make a plot and to the right-hand side I am writing the flexibility of some classifier. Flexibility is not a technical term. A technical term would be capacity, but I want to avoid the technical notions here. I just want to say that, for example, QDA would be more flexible, so quadratic discriminant analysis would be more flexible than LDA. Or if you do regression, linear regression would be inflexible, quadratic regression would be more flexible, cubic regression would be even more flexible, and so on. Now, we can plot the empirical error, the error on the training set, as a function of this flexibility. Now, if I just look at the empirical error, so the number of errors I make on my training set, it keeps going down with increasing flexibility of the classifier. So why would you not always choose the most flexible classifier possible? There is a generalization problem. There is something which I want to call, now let's say this is a tendency to overfit, or let me call this a false optimism, all of which are non-technical terms. And now the performance on a test set is the sum of the two. So typically we find something like that. This would be the performance on the test set. In other words, the quantity that we're really interested in. Or you can call this the generalization error. So the best classifier is the one that minimizes the sum of the two. So that would be the optimum flexibility of a classifier. Now, for the support vector machine in particular, the flexibility of the classifier increases with the inverse of the margin. So I could say I have 1 over the margin m to the right-hand side. So, you know, that's also what this picture about version space and so on tells you, or it is what note that here I've plotted 1 over m, whereas here I've plotted m. So in this picture here, my flexibility increases to the left, whereas here my flexibility increases to the right, because I plot 1 over m rather than m. So in the case of the support vector machine, if I have a wide margin, I have an inflexible classifier, and if I have a narrow margin, I have a very flexible classifier. Now, the empirical loss is something that we can measure on our training set, no problem. And I can indeed do that using, for example, the hinge loss with a parameter of m. What we do not have so far in our formalism is something that measures the tendency to overfit, or the false optimism, the red curve. And if we now decide on what is the proper margin, or if you want to decide automatically, we should take into account the empirical error and the tendency to overfit. Now, unfortunately, there is no simple mathematical formula for the tendency to overfit. There are some probabilistic guarantees that are related to the Vapnik-Chervonenkis dimension, a field called learning theory. But, well, these bounds are only probabilistic, and so if you ask different researchers, you will get different kinds of curves here. But everybody would agree that for larger flexibility, there is more tendency to overfit. Now, again, remembering that the axes have been inverted, because here the flexibility of the classifier goes to the right, and here the flexibility of the classifier increases to the left. That's what we have in this picture. So the black line here is the empirical error as measured by the hinge loss. And the red curve is a measure for the tendency to overfit. Or for false optimism. And now if you add up these two, you get out these green curves, which are our estimate for the actual error, for the generalization error. So for the green curve, let me write that this is all this bundle of green curves. Let me say that these are proxies for the generalization error. And I have a whole bundle of curves because I've used different weightings of the red curve versus the black curve. All right, and now the actual support vector machine is a mixture of these two. For an actual support vector machine, we already have seen all the empirical error, and we now add something that will quantify our tendency to overfit. So coming back to this formula here, this was given the margin M, but now I don't want to specify the margin M in advance, I want to find it. So I can instead do the following. I can say that I want to find the minimum with respect to W, B, and the slack variables of some function that depends on my normal vector or on the length of my normal vector. This is a capital omega. Oh, it's a lambda. And now note this void spot here. Nothing there, okay? It's maybe the most important thing about the formula. So I no longer specify the margin M. Instead, I have introduced a new user-defined parameter lambda. However, given this parameter lambda, I now solve this problem, where this thing here corresponded to the red curve that we've just seen. So this would be a measure of our tendency to overfit. And as you've seen in this plot here, it should be a function that increases with decreasing m, or remembering that m is inversely related to the norm of w, it should be something that increases with the norm of w. And indeed, what people mostly use is the following. The quadratic, so the squared Euclidean length of the normal vector. However, other choices are possible. And coming back to this picture here, so the whole false color plot here was the empirical error. So a function of w and in fact also of b. This was the empirical error. So this corresponded to the black curve. We now add to this another term, a function of the length of w. And the one important choice is the one that you see here. So this would be the squared L2 norm, or another choice would be to just take the L1 norm of w. And let me plot these two. So these are now the auxiliary functions that I'm adding, or the regularization terms. And if I use W transpose W, then these are the equicontour lines. So I'm adding something that increases parabolically as I go away from the origin. Whereas if I use the L1 norm, I obtain contours that look like that. And we will look at that in much detail later on in this semester. If you imagine adding this function to the empirical error, then you will see that this encourages solutions that lie somewhere on the coordinate axis. So this encourages primal sparsity, meaning that the normal vector will have some zero coefficients. This one is much more popular in the classification literature, and it is, amongst other things, very numerically convenient, but it has nice properties beyond that. Okay, and so after the break we will do the actual derivations of the optimization routine for this regularizer here. So this measure of tendency to overfit, this is the regularization term. Whereas the other thing here, the slack variables, this would be the data term. Okay, that's enough for 1 hour. Let's have a break. We had a problem with the audio recording, and this is why the following few slides, well, I will retell the story, but a little bit faster and without actually writing all this stuff, because it has already happened. So we have this formula where we have a regularization term and the slack variables and the constraints, and we now need to make a specific choice as to the nature of this regularization term. And typical choices are the quadratic norm of the normal vector, the quadratic length of the normal vector, or the L1 norm. Now, what people have used mainly for reasons of mathematical convenience is primarily this, and that's what we turn to now with the soft margin SVM. So the formula is just the same as on the previous slide, except that the regularization term has now been settled here as W transpose W. And the formula as it stands here is in the so-called primal domain. Now, with optimization problems such as these, so we have here a quadratic program, a quadratic objective function, and linear constraints, it would be perfectly okay to optimize it in this primal domain. However, it turns out to sometimes be beneficial to go to the dual domain, and I will say in a moment what this dual is. The reasons are that it is, or it can be more efficient if the number of features is much larger than the number of observations. So, say if we have 10,000 features, then each of these inner products here involving the normal vector will always involve, well, 10,000 numbers. And even after training, if we want to make predictions, I will always have to take an inner product between my observation, which will be 10,000 dimensional, and this normal vector. And in the dual domain, it turns out that, well, we operate with variables with as many variables at most as we have observations rather than features. In addition, we will discuss the so-called kernel trick, which allows to use all of this formalism that so far has involved hyperplanes only, to use this formalism also for nonlinear classification problems. Now up here, if these were equalities, we could use the Lagrangian formalism, but we have inequalities. And for inequalities, the proper approach is to use Karush-Kuhn-Tucker equations. However, most people just call these Lagrangians, and this is why we will also settle with this terminology in the following. So I'm setting up a Lagrangian function here, which involves both primal variables, the w, b, and xi that we've seen before, and new dual variables, the Lagrange multipliers. So I'm starting to copy here. This is the regularization term. This is the penalization of the slack variables. And now this thing here is turned into a constraint. So I'm saying these are in fact I equations, because I have one equation for each observation here. And I'm now bringing what is on the right-hand side to the left-hand side. So I have yi w transpose xi plus b, and then minus I plus xi. And I'm multiplying this with the Lagrange multiplier alpha I. And now since I have I equations, I sum over, since I have n equations, I sum over that many Lagrange multipliers here. Similarly, for the second inequality constraint, we introduce another Lagrange multiplier, or a set of Lagrange multipliers called mu, and I could have written here xi I minus 0, because there was a 0 on the other side of the inequality, but since multiplying 0 with mu will cancel, I've left it out. Now, this Karush-Kuhn-Tucker formalism tells us that if we want to look for an optimum, it has to fulfill the following properties. The Lagrangian, or this equation here, must be at a minimum with respect to the primal variables, w, b, and xi, and it must be at a maximum with respect to also at an extremum, but at a maximum with respect to the dual variables. And at this saddle point here, where it's minimal with respect to the primal, maximal with respect to dual variables, this is where we have our optimum, and I can indicate the optimum parameters by the superscript 0. These Lagrange multipliers that were introduced have to be non-negative, and we can now go on to find this extremum by differentiating this Lagrangian with respect to its primal variables. So we differentiate with respect to the normal vector and the bias and the slack variables, and we set all of these derivatives to 0. Now, starting with the first term, if we differentiate with respect to w here, well, this gives me a w, and there's another one hiding here, which gives me the sum over I alpha I yi xi, which you see here, and requiring that this be 0 gives me the following condition for my optimum solution, namely that the normal vector can be expressed as a sum over Lagrange multiplier times the observations, and that was the label of the nth, of the ith observation. This is an important equation which we will see again and again in the following. So, in other words, my optimum normal vector is just the linear combination of some of my original observations, and it will turn out that in many cases the sum is going to be sparse. So I don't need all training exemplars to express my normal vector. And this is one of the two attractions that I've mentioned earlier of working in the dual domain. Now we can differentiate with respect to the bias, and well, B appears just here, but it is multiplied with a yi and alpha I, and this is why I get a second condition that the Lagrange multipliers multiplied with the labels, which are either plus or minus 1, must altogether give 0. Finally, I differentiate with respect to the slack variables. They appear here, which gives me a C. They appear there, multiplied with alpha I, which gives me an alpha I. And they appear here, which gives me a mu I. Or altogether, alpha I plus mu I must equal C. Okay, so we have found the conditions that describe how we can find a minimum with respect to the primal variables. What remains is to maximize the Wolfe dual with respect to the dual variables. So I want to maximize with respect to the dual variables this expression, and you see that now these optimum values have already been inserted. So this is now being evaluated at the optimum, normal vector, and bias and slack variable. And we can now use this equation along with these equalities to produce the following. So I'm first starting to copy down here the 1/2 omega or W transpose W, which is here. And then there is a, well, this is already a collection of two terms. So we had the sum over the psi i's. Okay, I remember. Here we had this condition that alpha I plus mu I must be C, and there was a C here, which is now being replaced by alpha I plus mu I. Then in this expression here, alpha I times mu I times xi summed over index I will give me W. That was the equation here. So altogether, this term here is going to be that, minus W transpose W. Then we still have the term here, which depends on B. That's the one you see here. And those two, and that one. And we can now start and simplify a little. So we have W transpose W in these two places, which gives me that. And secondly, the psi I alpha I also appears here with a negative sign, minus sum over alpha I psi I. So this one goes away. And then we have psi I mu I and minus psi I mu I here, which also cancels, leaving us with this expression here. However, equation 2 had told us that the sum over alpha I mu or yi has to be 0. So making that entire part 0 also. And what survives is just here the term quadratic in W and the sum over I alpha I from this surviving 1 here. And this is subject to the equations that we had here and to the dual variables being non-negative. Now, using this equation here one final time gives us the following. So we replace W by the sum over I, yi alpha I, xi, and the second W similarly, but using a different index here, using index j. So this expression here can be rewritten as follows. Okay, and then here are these constraints. These two, together with equation 2 from the previous page, can be combined to say that the Lagrange multipliers alpha I, they anyway have to be bounded below by 0, but they must also not become larger than c, which was the user-defined constant that we put in to trade off the regularization versus the data term. Okay, now this is the optimization problem that we need to solve. This here is a little redundant, or all of this is summarized in this equation here. And in fact, this can be written even more succinctly as follows. To bring out even more clearly the quadratic structure we have. So this is also a quadratic objective, just like we had in the primal. Here we have a product of two dual variables, alpha I and alpha j. But we can write this whole thing in matrix form as follows. So rather than maximizing, we may wish to minimize, to put this in the standard form for a quadratic programming problem. Then we have to invert the sign, of course. And now here we had an inner product between two vectors, xi, xj. I'm inserting these inner products, I'm collecting all of these inner products in a kernel matrix. So the element ij of this kernel matrix is going to be xi transpose times xj, which is written here. Then I have these vectors alpha summarizing all of my Lagrangians, my Lagrange multipliers, and I actually have a missing term here. The sum over the alpha I can be written as 1 transpose alpha, where this is a vector of all ones. The one thing that I've not mentioned are the y's. I can collect these in a diagonal matrix that is holding the n labels, which must be +1 or -1, along a diagonal. So now this is something that you can put into any standard quadratic programming solver. Specifically, I have here underlined in green the different inputs that you need to provide. So this is what you want to solve for. But the y's, the labels, are given in the training set. The kernel matrix you can compute using this recipe. And C is a constant supplied by the user that will specify how strongly do we want to regularize, or how closely do we want to fit the data. Okay, so this you can really put into a solver, and once you've done that, you get out a collection of alphas. And now how do you relate them to the solution in the primal domain? You can again remember that your normal vector W is simply sum over I alpha I yi xi, and after optimizing for the alphas here, you can insert what you found, and thus get the normal vector in the primal domain. Now I mentioned earlier that perhaps we don't need to involve all of the observations, and indeed this is one of the interesting, perhaps the most interesting feature of support vector machines. And the reason is given by this Karush-Kuhn-Tucker condition. I'm not going to explain in detail, but this is in the theory of optimization. This is a condition that's otherwise known as the complementary slackness condition, which states that the product of a Lagrange multiplier and the equality or inequality it tries to enforce, that the product of these two has to be 0. Now, for this product to be 0, obviously one of the two factors has to be 0. And let's look at these in turn. This is the Lagrange multiplier that we get out. This, on the other hand, well, that was the score, so how much I was lying on the correct or wrong side of the decision boundary. This is -1, the margin that I want to subtract. And if a point lies on the right side of the margin, then this thing here cannot be 0. Okay, if a point lies on the correct side of the margin, then it will have no slack. No slack is required. And remember that slack appeared in the primal objective function, and the program was explicitly asked to minimize it. So this thing will be 0, and this will be some number larger than 0. So I've plotted a small example here. This is a positive and a negative class. The minuses show samples of the negative class. I have a decision boundary, and all points which lie on the correct side of the margin, so those positive points out here, or the negative points out there, they will have factors here that are non-zero. Now, for this equality still to hold, then obviously their Lagrange multipliers have to be 0. And this is exactly what makes for sparsity, what this very interesting property of support vector machines. So the slack of a couple of variables I have indicated here. So this would be amount of slack or the distance that this point has from the correct side of the margin, or that positive point has from its side of the margin. Here's the slack for two examples from the negative class. This is not an optimum solution, by the way. I couldn't figure it out, out of my head. So the real true optimum decision boundary would lie somewhat differently here. But the important point is that my normal vector W will now be specified as a linear combination only of the support vectors and not of these other points out here. So let's look at an example. This was a training set that's linearly separable. And on the one hand, if we step back, we see the red points are on the right and the blue points are on the left. So we could argue that the optimal classifier should perhaps simply be something close to a vertical line, somewhere in the middle. And indeed, we have down here a solution that's pretty close to what I would think is reasonable. But since the data set is linearly separable, we can also find a classifier here, in fact, of maximum margin that is compatible with all these observations. So this is an extreme point inversion space. Version space was the space of all possible classifiers. Version space was indicated here. In this plot that showed the empirical error as measured by the hinge loss of different classifiers that all go through the origin but are parametrized by W1 and W2. And this was among all classifiers from version space, the one with widest margin. So among all classifiers that give 0 hinge loss, this was the point. Widest margin means shortest normal vector. This was the point that was closest to the origin. And here, on the other hand, the user put in a smaller penalty on the slack variables, and that resulted in a much wider margin, but also here in a larger number of support vectors. And well, we can now, by varying this parameter, this penalty parameter that you saw, can look at a few solutions that will result. So for decreasing penalty on the slack variables, you see that the classifier rearranges so as to get a margin that becomes wider and wider, and at some point the margin jumps to the next further observations, and you see that we start having more and more support vectors. Now, these support vectors, they had an upper, we saw that support vectors, or the Lagrange multipliers, they have to be larger than 0, but they have to be smaller than this user-specified parameter. And what we saw initially was that here the Lagrange multipliers were still smaller than this upper limit, and at some point they can no longer offer resistance to the margin, so the margin grows beyond these support vectors, at which point these Lagrange multipliers now have assumed their maximum values. So all the support vectors that lie inside their margin have their Lagrange multipliers set to the maximum value. This was the maximum amount of resistance, if you so wish, that they could offer to the advancing margin. And at some point the margin gains the upper hand and continues and pushes past these support vectors. Now, in terms of this plot here, when lowering the penalty on slack variables, it implicitly meant that we are trying to regularize more, and that means that the solutions that you have just seen, they have been tracing out. It means that effectively I have reduced this region of tolerance, or I have reduced the domain from which I want to select an optimum solution. And the solutions that you have seen have traced out a path from this extreme point, from the hard margin SVM to well, a pretty strongly regularized solution in the end. And the path here along, the path that we have traced out here was a path of increasing margin. So here you see the margin, and plotted here in black is the empirical error that you find. So while we are in version space, we have 0 error. But if we now force the normal vector to become shorter and shorter, we start seeing larger and larger empirical error as measured by hinge loss. And well, here's always the same quadratic regularization term that was used. And by now weighing these two terms with different coefficients, so by adding the red plus a constant user-chosen constant times the black curve, I obtain this set of green curves, and our quadratic optimizer always finds the minimum of each of these. And these are the solutions that you have just seen. To put this in relation to a plot that you've previously seen, the axes here are inverted in the sense that here the flexibility of a classifier increases to the right, which means narrow margin. And in the plot that you had just seen, the flexibility increased to the left because the margin was plotted from 0 to some larger value. And what we had was, on the one hand, the empirical error as a function of the margin, and the narrower the margin, the smaller the empirical error as measured by the hinge loss. And at the same time, we have a regularization term here shown in red. And if I now build a weighted sum of the two, it means that effectively, I can rescale one or the other. But overall, I get something that imitates the performance on the test set, or the generalization error, which is shown by this curve here on the top. And a proxy for this true generalization error is a so-called cross-validation error, which I've also shown here, where the training set is partitioned into a few subsets, and the algorithm is trained on some subsets, and the prediction is made on the one that has been left out, all with the aim of estimating how well the method will generalize later on. Okay, so so far we have seen how, when we use a quadratic penalty as regularization term, how we obtain something that can be put into a form that standard quadratic program solvers accept. And the last thing here of interest is that this kernel matrix here, it is just a measure of similarity. So this kernel matrix, also called the Gram matrix, it's an n by n matrix if I have n observations. And the way we have worked so far, its ijth element is given by the inner product of observations or feature vectors I and j. However, we can think of other similarity measures. In particular, for non-vectorial data, you will want to use other similarity measures. The only thing that they have to satisfy is that this matrix K should remain positive semi-definite. Because as long as it is, we have a convex optimization problem and a unique optimum. If this matrix is not positive semi-definite, then optimization would become much, much harder. Now, in the following, we will see how to exploit the fact that we have the freedom to use other similarity measures here. We will see how this freedom of choice can be used to apply the support vector machine, which so far was just a linear classifier using a hyperplane, how this classifier can be used also for non-linearly separable data.